Okay, lecture 4. We are talking about our star, which is the sun. Um, these are slides 10 through 14 on the second PowerPoint that stars the sun and the moon. As you can see with all of these visuals and this great Nat Geo Sun 101, which we highly recommend you watching. So please make sure that you play that. Um, the sun is something that we're super familiar with. It's the details, as it is with anything that we're looking to expand upon here in our very brief overview of the structure of the sun and some of the details about it. Um, a lot of the minutia is not a concern. So as you go through your notes, I'll be emphasizing the things you do want to highlight or notate. But a lot of things are just really kind of cool and interesting to learn about. And had we been together in class, we'd be going into great detail with those. So we'll keep it to a minimum for now. Just want to talk about one picture, which is this one right here. And this is just a portion of the surface of the sun. And you can see here one of the eminences here kind of, bursting off. That's hot gas plasma shooting off the sun. And just right here, this little teeny tiny thing, which you may have missed, that little guy right there is Earth to scale. So in terms of the size of our planet, the whole thing in comparison to just a fraction of a plasma outburst from the sun is minuscule, to say the least. So it's very difficult to just picture how massive the sun is when you look up in the sky. And sometimes it doesn't look that big. It is the most massive thing in our solar system. And that being said, it's actually only a medium-sized star, so it kind of comes in as average. There are smaller stars than the sun. There are way bigger stars than the sun. So it comes in at about the average. Its diameter is 1.4 million kilometers, which again is pretty huge. And again, that's about 100 times the Earth's diameter. So you could fit 100 Earths all the way across the diameter of the sun. The two main gases you'll find in the sun are hydrogen and helium, as you would find in any other star. It has multiple layers, which we'll take a look at momentarily. Please highlight what is underlined here for you. Almost the entirety of mass that is present in our solar system. So that is all of the planets, all of their moons, the asteroid belts, the comets, the asteroids, the icy rock bodies, everything else that is in our solar system makes up 0.2% of the mass. The sun is almost all of the mass in our solar system. So again, one of those concepts that's kind of hard to grasp. It is huge, okay? And then lastly, the sun's about halfway through its life cycle, halfway through its hydrogen stores, puts it at about 5 billion years. It's been here for about 5 billion years. It'll probably last for another about 5 billion years before it kind of goes into the super death mode as well. Okay. So how does the sun produce its energy? And this, again, this process of the sun's energy production is exactly the same that is happening in every other star you see in the night sky. So here's this reminder about how fusion works, right? We have two small nuclei, here's two hydrogen atoms, and they are being forced together because the temperature and the pressure is so incredibly high in the sun's core that it's forcing these two nuclei to smush together and become a nucleus that now has two protons, which, if we remember from chemistry, is the next element on the periodic table, which is helium. And so that is the process that is happening. The temperatures, in order for that to happen, have to be roughly around 27 million degrees Fahrenheit. Again, a number that's kind of beyond comprehension for us because, boiling water, is 100 degrees Celsius, 212 Fahrenheit, and that scalds us. Water cooler than that, frankly, scalds us. So the idea of 27 million degrees Fahrenheit, again, is astronomical, literally. Again, based on the size of the sun, it's got enough hydrogen to last for roughly about 5 billion more years. So we won't be here when the sun kind of goes into its death throes, if you will. Let's take a look at some numbers, though. All right, here's how much huge amounts of mass, millions of tons of mass able to be converted into energy. And that's the energy that we see and we feel when we feel the sun's rays and we see the sunlight. As we have talked about before, the sun is the Earth's primary source of energy. Again, another link here that you're going to want to check out to further your understanding or for any clarifications. Right? What we have is referred to as the solar constant, and that's basically a set amount of energy that reaches essentially the atmosphere of the Earth on a regular, steady basis. Estimated that's a little over 1,000 watts per meter squared, which is basically the same amount of energy as you would have from 100-watt light bulbs in 1 square meter. Right? In other words, it's a lot of energy. Okay. Basically, every single energy process that happens on our planet is the result of the sun. All of these cycles that we see pictured here, carbon, the water cycle, respiration for plants, photosynthesis for plants, fossil fuels, and the burning of those, all of those processes are the result of the sun's energy and that solar constant that we receive. Right, very briefly here, you've got some vocabulary in terms of the layers of the sun, so the structure. I'm going to talk about these terms that are located over here by looking at this picture located down here. Okay, so deep within the center of any star, and particularly our sun, we have what's called the core. That's where fusion is occurring. All right, you have basically huge amounts of energy that's being radiated back out until you reach what's called the photosphere. That is where the light is seen from the sun, or AKA the surface of the sun. You have a couple different atmospheres here. You have an inner atmosphere called the chromosphere, and that's basically consisting of very, very hot gas. And then you have what's called the outer atmosphere. Oopsies. You have what's called the outer atmosphere, which is the corona. Ironic choice of words at this time, but it is the corona, and it is what we typically see during an eclipse, which you can see pictured here. Okay. Then you have a couple other interesting aspects to the sun. They're not part of the layers, but they're some of the features of the sun that you see when you look at them. One are called sunspots, and they are cooler, darker spots that you find. So we can see a few here and a couple up here. All right, so some cooler, darker spots located on the surface of the sun, so on the photosphere. You have these things called prominences, which you can see over here on the left, and that picture I showed you on the first slide. And that's basically basically hot gas and plasma that shoots out from the photosphere and extends beyond the chromosphere into the corona. And then you have what are called flares, and that's basically a huge amount of radiation that gets released from the sun on rare occasions, and that can have a lot to do with different temperature and pressure buildups located within the sun's core and on its surface as well. And lastly, we have something called auroras. In the north, they're called the borealis, and in the south, they're called the australis. But they're basically these kind of beautiful pictures that the night sky provides for us. And they are the result of interactions between electrified gas and solar wind. Okay, so what happens is we have a lot of high energy electromagnetic radiation, aka light, coming from the sun, and that high level electromagnetic radiation essentially electrifies. It interacts with gas particles that are located in the atmosphere. So depending on the gas particle, nitrogen, oxygen, carbon dioxide, etc., depending on the interaction of those molecules, you end up with a different color scheme, right? Yellow-green is the most common because nitrogen is the most common gas located in the atmosphere, but you can get all sorts of different colors with the aurora borealis, and I'm sure if you start Googling them right now, you will see lots of beautiful pictures. The borealis can only be seen in very northern places, Alaska, northern Canada, Norway, Iceland, things like that. And then obviously the borealis are seen found in Antarctica and in some places of Australia as well. Those are our notes on the sun. Please make sure that you notate the things that are colored and underlined. Please make sure you answer end lecture puzzle question and complete your after lecture activity. Again, as always, please make sure that you are emailing and contacting Ms. Case and I if you have questions, going up to Google Meets for during our office hours, and as always, checking the LPHS website for any additional information. Hope to see you all soon. Take care.